Hey everybody, it's the Monaco again. On our second homework video, we are going to hit up our vocabulary today. So the special words of the periodic table. And I'm going to follow this up with a Google Classroom assignment, like pre-assessment like last unit. First word of the unit is ionization energy. And this is a graphic showing the actual values for ionization energy of all the elements. But what does it mean? Well, ionization energy is the energy needed to remove the first valence electron. So if you want to think about it like I do, it's how hard the atom or the element holds on to its one valence electron or one of its valence electrons. Okay, it's a very important value. Electronegativity. It's our second term. Again, a nice graphic showing you all of the actual electronegativity values. They scale from 0 to 4, and the noble gases aren't even included. This is, again, a measurement of the ability of an atom to attract another electron. So while ionization energy is how hard an atom holds onto its valence electron, electronegativity is how thirsty or hungry it is for somebody else's electrons. Atomic radius. Well, atomic radius is a good measurement of how big atoms are. And for this particular example, the radius of an atom is measured by half of the bond length of a diatomic molecule of that element. That's just classically how it's determined, but generally what atomic radius means is what radius means for any circle or sphere. How big is it? Ionic radius. Well, here's a good example and a picture of the sizes of atoms and their corresponding ions. Okay, so a lithium positive ion has an atomic radius of 90, and the lithium atom has a radius of 134. For example, so that's how you understand this particular graphic. The left-hand side is for the reds or the ionic size, and for the right-hand side, the blue is the ionic size. So as you can see, some atoms get smaller when they form ions. All the positively charged ions are smaller. And some atoms get bigger when they form ions. All the negatively charged ions are bigger. So here's our classic definition. Radius of an ion. Does it get bigger or smaller in relation to the atom of that element? That's what you got to know. Positively charged ions are smaller than the atom that formed them. Negatively charged ions are larger than the atoms that form them. Next set, chemical reactivity. So this is a good graphic that shows metal reactivity and nonmetal reactivity. And what it's telling you really is that behavior of the element based on the number of valence electrons and the number of shells. Certain elements are more reactive than others, and it all depends on their valence electrons and shells of electrons. Metallic character. As you can see in this particular graphic, metallic character changes in different directions. This graphic covers metallic and non-metallic character, so let's see what our definition is turning out to be. It's the ability of an element to readily lose electrons, have a luster, conduct electricity, and be ductile and malleable. In layman's terms, how metallic does this element look? Is it shiny like a metal or is it not? Does it conduct electricity like a metal or does it not? Etc. So the word character there shouldn't mess you up. It's just a characterization. Non-metallic character. So how not metallic something is. And here's our definition. The ability of an element to attract electrons, to be dull, not conduct electricity, be brittle, all of the above. Okay. Metals. 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 Clicker. There we go. Copper, lead, tin, zinc, steel, nickel. There's a lot more metals than just here in this picture, but a metal are elements that lose electrons. They have a shiny luster, they do conduct electricity, they are ductile and malleable, and they can be found to the left of the staircase on our periodic table. Here we go. More vocabulary words. Metalloids. Metalloids, there's 8 of them. Depending on what chemist you talk to, there's 7, but there's 8. And they are special elements that have a mixture of metal and non-metal properties. They are often found along what we call the staircase, which is just a zigzag line on the right-hand side of your periodic table. It's there strictly to remind you of which elements aren't quite metals and are not quite non-metals. They are metalloids. Non-metals. Non-metals are all in yellow in this particular example. There are fewer non-metals than metals, but there are more non-metals than metalloids. Okay, nonmetals are elements that attract electrons. They are dull. They do not conduct electricity or heat. And they're often brittle or found to the right of the staircase. They're brittle or gases usually on that periodic table. Alkali metals. This is a special group, special family. The one that does not truly belong to the alkali metals is hydrogen. Okay, notice we didn't name it in this particular example. So lithium, sodium, potassium, rhodium, cesium, francium. Alkali metals are any metal from group 1. They all have one valence electron. And hydrogen is not technically considered a metal. It's floating above the periodic table. It's not really part of this group. Okay. Alkaline earth metals. This is a true, genuine family of elements. Beryllium, magnesium, calcium, strontium, barium, radium. Any element from group number 2. They all have 2 valence electrons, and the way to remember it is the alkaline earth is 2 words. So group 2, 2 electrons in the valence shell, 2 words. The number 2 is kind of a catch. It tells you where to look and what to think. Okay. Halogens, another special family. This is a true family from group 17. So we skipped groups 3 through 16 because they're mixed families. We're going with the purebred families here. Group 17, fluorine, chlorine, bromine, iodine, and astatine, I believe. Antimony. Anyways, group 17 elements, they all have 7 valence electrons and want 1 more electron to complete their outside shell of electrons and become electrovalent, same electrovalence as the noble gases, which is the last group in the periodic table, group 18. Helium, neon, argon, krypton, xenon, and radon. These ones, group 18, all have 8 valence electrons. It's a full shell, and they are very unreactive as a result. Helium is technically considered part of this group, even though it has 2 valence electrons in its outside shell. It's a full shell, even though it's only got 2, because that particular shell only holds 2 electrons. The transition metals. So we skipped all these groups because they belong to one big extended family. Okay, it's mixed, it's blended, it's huge, huge, Rochester, huge. The transition metals. It's going to be huge. It's going to be great. They form from groups 3 through 12. The properties may vary, hence an extended family. Not everybody looks the same there. But they do form colored solutions. So compounds of transition metals make nicely colored solutions, waters, liquids. Okay. Periodic law. I am the law. Okay, some Judge Dredd action there for you. These are the physical and chemical properties of elements become predictable when they are arranged by atomic number. So the periodic table being arranged the way it is today reflects the periodic law. We've arranged all the elements into columns and rows that make their properties and their behavior predictable just by looking at the periodic table. Periodic law made the periodic table possible. Periods, simple enough. These are the rows on the periodic table. They are across from left to right. They all have the same number of energy levels. So if you're in period 3, you have 3 energy levels of electrons. Period 4, 4 energy levels, etc. Period 5, 5 energy levels. 6, 7, 8. Well, there isn't a period 8, but if there was, it would have 8 energy levels in it because the periods relate to the energy levels. The groups and the families, they're synonyms. These are the vertical columns, okay? There's only 6, 7, 8 or so properly named groups, and we've got down the periodic table. They have similar properties because of the same number of valence electrons. Those are the tightly knit families where all the properties are similar to the same. The other family, the transition metals, again, is extended because there's that rule, the same number of valence electrons doesn't really apply to them. Diatomic elements, there are 7 of them. Memorize them any way that you can. Okay, use the acrostic here, or just memorize the 7 elements that are diatomic. They're special, only found in groups of 2 in nature for reasons. We'll leave it at that. Allotropes, I believe this is our last word. It's a very unique word to the element carbon and the other element sulfur. And what it means is that one element can take different forms based upon how the atoms are connected. And that's what that long definition means. These are substances made of the same element, but have different properties because of the different way the atoms are arranged. So graphite and diamond, one's extremely valuable, one's extremely not valuable, but they're both made of only carbon atoms, and what makes them different, and then hence their difference in value, is how those carbon atoms are connected to each other. And that was it. Okay. So the next video is going to be about the history of the periodic table and law. This video, there's a Google Classroom assignment attached with it. It was just a pre-assessment of the big overarching themes in the unit. So thanks for taking your vocabulary. Remember to study them for our vocabulary quiz. Hasta la pasta.